Hello everybody, welcome. Today we are going to discuss the solution to the problem maximum product of splitted binary tree. It's a medium rated problem and the problem statement itself is a bit convoluted, but we're going to get to it and dive into a more visual approach to the solution. Okay, let's talk about the problem itself. The input is a simple root of the binary tree and the output is a simple int. Now this int is what makes this problem very interesting because this int is the maximum product of the sums of two subtrees. Okay, let's take an example first. Let's say we have the example here in the list of examples on LeetCode itself. And what you're going to do is you're going to take this binary tree and you're going to make a cut. You're going to make a cut, let's say between 1 and 2. Now when you make a cut, this entire tree, this entire binary tree gets split into two parts, 245 and 136 as shown here. Now this is the first step. The second step is taking both of these splitted out subtrees, both of these trees now, and compressing them. And now the way you compress them is by simply taking their sum. So 1 plus 3 plus 6, sum 10, 2 plus 4 plus 5 gives a sum of 11. And you're going to store that. Now, the real value of this particular cut is going to be 11 times 10, is the product of the sums of the binary subtrees. And the goal is to return the maximum possible product of the sums of the two subtrees. Basically saying that, this edge was happened to be the answer, but there are n nodes in the graph, n nodes in the tree, and so n minus 1 total edges. This means that there are n minus 1 possible cuts and you have to find the best possible one. Okay, let's talk about this again, but this time we'll take a more organized approach. The goal is to find the maximum product. That's fine. What we can do is, thinking naively, is just that there are n nodes in the tree, so there are n minus 1 total cuts. Let's just enumerate all the cuts and see what works out the best, right? More formally speaking, we're going to take the maximum possible of, for each node in the graph, for each node in the tree, we're going to find for each cut in the node. So a node has its left and right subtrees. We're going to try cutting both of them and we'll get their scores. Whichever is the greatest, we're going to store it in the maximum possible value. And we're going to do that for each and every single possible node, for each and every possible cut, which is just right and left, and get their scores. Okay, now how do you go over all the nodes? It could be as simple as DFS, and that is what we're going to use here. The second part cut is a bit more interesting. Let's take the case here. You can see this tree here, and I've labeled it with uh, letters instead of digits. This part is not really that important right now. Let's focus on the letter B. Let's say this yellow node is the current one I want to focus on and get its answer. Basically, tell me if cutting the left subtree or the right subtree is beneficial. Whichever gets me the biggest score is what I'll store. Pretty cool. Okay, let's try cutting the left subtree apart. This splits it out into G and D here and this entire area in purple. Now again, what was the goal now? You want to take the sum of G and D and whatever the area is in purple. You're going to take both of them and multiply them together. This brings us to the third point, which is saying that when you cut the left subtree, you take the left sum multiplied by the total minus left sum. I want you to think for a second why it is not left sum times the right sum. I made that mistake initially and it's a very dumb mistake, but it's a mistake nonetheless. So it's left sum times the total minus left sum. Left sum is something we can get here in the recursion easily. And now what's remaining is the total minus left sum. Pretty easy. To find that total, however, is another story. How do you find that total? One way you can do is by just doing another DFS. That is exactly what we're going to do. One DFS to find the total and the other DFS to go ahead now and explore each of those nodes and get me their best possible answers. Okay, let's go back and let's try to code it up. So we need one DFS to find the total. Let's call it get total. and this is going to take an input as the node. Now the get total is going to return a particular integer value, so we're going to keep that in mind, and we're going to save total as get total, and we're going to pass in the root. Okay, what's the base case for this recursive function? When the node is no longer valid node, basically saying if not node, return 0. 0 because the return type is an integer. Okay, if the node is a valid node, then we want to explore its left and right childs. So let's go ahead and explore the left child. We'll do it by get total of node.left. Pretty simple. We can do the same for the right child. Now, how do you actually get the total? Well, you'll take the total from the left subtree and the right subtree, add them to the current node value and pass it on over. So we're going to return the current node value, the left tree's answer and the right tree's answer. As simple as that. Now let's come to the second point of the solution, which is saying, basically let's have a self.answer. We'll start off with 0. And now we want to do our DFS again. So we'll actually call this DFS now. And what are we going to return here? Well, let's not return anything where we have this self.answer storing the maximum possible anyway. So no need to return anything. And so we'll write the base case as if not node, return nothing. But at the same time, it's important to know when you are, say, at the node B, you want it to return this thing, this sum here, so that you can compute the left sum and the total minus left sum. So instead of returning nothing, let's actually make it return something, even though we're storing the answer in self.answer. Now self.answer is the max of self.answer, comma, what. First, we want to find the answer from the left subtree. This is basically saying what happens if I cut this left subtree apart. Basically, this red line over here. So we'll do left equals to DFS of what? Of node.left. And yeah, that's it. This will get you the left answer. And you can now say that, okay, whatever the answer is, I want to compare it with left times the total minus left. But this is just cutting the left subtree. Let's also cut the right subtree apart. This is going to be another case where we say, okay, instead of left, let's just consider the right as well. So we're going to store that again, and we're going to say right times total minus right. Okay, the brackets are fine now. Cool. And what do we want to return here? See, answer we're storing anyways. What we really want to return is the current node value, the left, and the right. If you notice something, these two functions look very much similar. In fact, we're going to compress that in a second, but first let's get this running. So we'll return self.answer by running DFS of root. Let's do a quick sanity check. Okay, great, it works. I'm not going to submit it just yet because we can actually just do this. Okay, wait, what happened? See, this function is not at all necessary. If you look at each of these steps line by line, this is just what we're doing in this DFS function. So you can just call DFS again. Is there any difference? Nope, there is not. This is very dumb, but this is the solution. What can I say? Pretty cool too. You can just compress two functions into one because they look too similar. We'll actually have self.answer as 0 here, and we'll also have total as 0. This is just an implementation level caveat, you can say. Cool, let's do a quick sanity check again. By the way, this does not destroy the self.answer even though we are doing two DFSs. Okay, let's submit this and we'll talk about the space-time complexities. Okay, oh no, that was a painful error. So the question says that because the answer can be too large, return it modulo 10 to the power 9 plus 7. I made that mistake a lot. So we'll do that. Uh, Modulus 10 to the power 9 plus 7, and we'll just submit this again. This cool. Let's talk about the space-time complexities now. Okay, what's the time complexity? We're looking over each node, and for each cut get score. Basically, the goal is to do a DFS. We're doing that DFS twice, and that just means the time complexity is order of 2n. Now, if you also look at it, there are just two variables, self.ans and total. And yeah, all of these are just simple variables. So you would think that the space complexity is also order of 1, but it's not. Why is it not? That's because of this recursion itself. This recursion itself is going to take some memory in the stack of the program. What that means is, however large the tree is, that large is going to be the size of the stack, or equivalently the space complexity. If the size of tree or if the height of the tree is order of n, then the space complexity is order of n. If the height is log n, is going to be log n space complexity. Both of these cases are, by the way, when in case it's order of n, which means that basically the binary tree is degenerate. There's just a case of like one element here and then one here and one here, and just on the left hand side there are multiple elements, nothing on the right side for any node. That's one degenerate case. However, the best possible case is when it's like perfectly neat and clean balanced binary tree, in which case the height is now log of n. Cool. This is the solution for the problem maximum product of splitted binary tree. If you have any questions, suggestions, feedback, let me know. And I'm going to be posting more regularly, in fact, every single day, as it has been for over 21 days now. So I'm hoping I can keep up the habit. Subscribe and like, please. That's it. Cool.